Myself, Mr. Rahul Chakule. I am presenting you the problem of slider crank mechanism by using relative velocity method. Already you know the rule number 5 is having two graphical methods. First, relative velocity and acceleration method. Second, ICR, that is instantaneous center of rotation. So instead of solving the problem by relative velocity and acceleration method, initially I am taking slider crank mechanism problem by relative velocity method to understand how to make the velocity polygon in a better way. In previous video, we have discussed the 4-bar mechanism problem by the same relative velocity method. Now let us see the problem of slider crank mechanism by relative velocity method. In given problem IC engine mechanism shown in figure, the rotation of crank is given 600 rpm in clockwise way. The position of crank is given, that is 45 degree from IDC, inner dead center. The length of crank is given AB 0.5 meter and the length of connecting rod BP is given 2 meter, and on given connecting rod BP a point capital D is lies at a distance of 0.5 meter from capital B. So from given information for a given IC engine mechanism, unknown is velocity of slider P, second unknown is angular velocity of connecting rod BP, and the third unknown is velocity of point D which lies on connecting rod and which is at a distance of 0.5 meter from capital B. So before making a velocity polygon, the different basic steps are given that we had discussed in previous problem. First of all, you draw the same mechanism with the help of scale. So again, you take the scale for configuration diagram which is drawn by using the scale. So this particular diagram is called as configuration, or it is also called as space diagram. So for making this configuration diagram, I have chosen the scale as 1 centimeter is equal to 0.25 meter. So again, based on the length of the link, that is a minimum value which is for crank 0.5 meter, and the maximum length of the connecting rod which is 2 meter, and available space on which you are making the velocity polygon. So considering all these things, you take the scale for configuration diagram. Here I have taken the scale is 1 centimeter is equal to 0.25 meter. So after making the configuration diagram with the help of scale, the next target is to make the velocity polygon. So before calculating the velocity polygon or before making the velocity polygon, it is required to take the scale for velocity polygon. So again, this scale for velocity polygon you can take on the basis of velocity of crank, because for a crank the RPM value is given, the length you know. So based on the velocity formula, which is velocity is equal to R into omega, where R is the length for the given crank and omega for crank is given. So it is 600 rpm. So based on this rpm value, that is rpm, and you can easily determine the velocity for crank. So V is equal to R into omega, Omega you don't know, that is angular velocity for crank, but you can easily determine by using the basic formula 2 pi n divided by 60. So RPM you know, so by keeping the value of RPM, you will get the omega value for crank. You keep this value of omega in the equation of velocity, and you will get the velocity of AB, that is velocity of crank, is equal to 31.41 meter per second. So based on that velocity, you can take the scale for velocity polygon, and here I have taken the scale 1 centimeter is equal to 6 meter per second. So after deciding the scale for velocity polygon, let us see how to make the velocity polygon. So first of all, you fix the fixed point. Here A is the fixed one, so you locate the fixed point, that is capital A, here as small a. So while making the velocity polygon, always try to give the notation as small letter. So here capital A is the fixed point. So here I have given the notation of small a. Now, of course, particular link is a scalar. It is both having a magnitude as well as direction. So magnitude, you know, it is by already we have determined, and direction. The direction is, it is always perpendicular to link. Okay, so here AB is the link given in the problem, and accordingly you take the perpendicular, because the velocity is always perpendicular to link given in the configuration diagram. So here I have taken the velocity of crank perpendicular, which is given a clockwise. So based on the clockwise way, I have taken the length small ab of particular length in this particular way based on the direction of rotation. So how much length I have taken? It is again the velocity of that crank that we have already determined, divided by scale, that is a 6 meter per second. So the 31.41 divided by 6, that is approximately 5 point something length. So you take the length of 5 point something length, that is the vector small ab, which is the magnitude, and the direction already the perpendicular to velocity. In that way, because the crank is moving in clockwise way, so I have taken a as the left side and small b on the right side. So after the finding the magnitude as well as the direction for crank, the next link is the connecting rod, that is bp. So how to determine the velocity of link bp? Again, you don't know the magnitude because the omega for connecting rod is not given, but you know the direction. The direction of connecting rod, it is always perpendicular. So you know the B point. You don't know the P, that is a slider. You have not located the position of P point till a time. So you know the point B. So the velocity of connecting rod, it is again perpendicular passing through the small b. Now how much length should I take? I don't know the magnitude for connecting rod. So but I know the direction. So from small point B, I have taken the velocity perpendicular to link capital BP. So leave that. The next link is the slider P. So you know the slider is always sliding along the line of action with respect to the fixed point. So from the fixed point A, you take the straight line, that is the stroke of the slider, and this particular line of action of the slider and the velocity line of connecting rod where it is intersecting, you give the notation as small p. Okay, so the small p you got. Now the point D, which is again lies on connecting rod, it is at a distance of small 0.5 meter from capital B. So again, you have to locate the D point on the velocity polygon as we have located the D point on the configuration diagram. Now how to locate the point D on the velocity polygon? There is a one proportionate method, that is the capital BP, that is a larger length divided by BD, that is a smaller length, is equal to same value, that is small BP divided by small BD. So this capital BP divided by capital BD, this particular is from the configuration diagram, and this particular small BP and small BD, it is related with the velocity polygon. So out of that four parameters, the capital BP and capital BD, it is given in the problem. Then small BP, the small BP you can easily determine from the velocity polygon, because you know the vector small BP into scale, that is nothing but the magnitude for the BP divided by BD. So from all these four parameters, the three is known and one is unknown, that is BD. So BD is equal to 0.925 centimeter. So always then you take this 0.925 centimeter length from B on the connecting rod. So from point B, from small point B, you take the length of 0.925 centimeter along the connecting rod. So you will get the point D. So you connect this D point to the fixed point A, and that is nothing but the velocity of D point. So this is and we have written the notation, that is velocity of B, then velocity of P with respect to B, and then velocity of slider, that is velocity of P with respect to fixed point. So instead of writing the velocity of P with respect to A, you can also write down the velocity of P. Now this is a velocity polygon. Now based on the velocity polygon, let us go for unknown. So here first unknown is the velocity of P. So again the velocity of P, it is nothing but the vector small ap. That is, you take the length of small ap vector and you multiply by, because this length ap is in centimeter and velocity is always in meter per second or centimeter per second. So you multiply by scale. So 4.4 centimeter is the length for vector ap. You multiply by scale, you will get the 26.4 meter per second. The second unknown is velocity of D. So again, already we have done, or we have connected the D point with the fixed point. You measure the length small AD and you multiply by scale, because the length of small AD in centimeter and always velocity in meter per second. So you multiply this length of AD by scale. You will get the answer 28.8 meter per second. And now the third unknown is the angular velocity of connecting rod BP. So by default, you know the velocity is equal to R into omega, where velocity is velocity of BP is equal to length of BP into omega of BP. So out of this, the omega is unknown, but velocity of BP you can easily find out with the help of or from the velocity polygon. So the velocity of BP, it is nothing but the vector BP. So you take the length of small vector small BP, you multiply by scale, then you will get the velocity of BP, that is velocity of connecting rod. And length of BP, it is already given in the problem. So by keeping these two values of velocity and length, you can easily determine the omega of connecting rod. So the omega of BP is equal to 11.1 rad per second, which is counterclockwise about B. So in this way, by making the velocity polygon and based on that, we can solve the unknown asked in the problem. So thank you. This is over.